Okay, we got all our little stuff up. Okay, so good, we're good to go. All of our technology is in order. What is, except for that part. The midterm is Tuesday, March 9th in person, or Wednesday, March 10th by Zoom. You should have made an appointment with me if you want to do it by Zoom. If you want to do it in person, it will be in the engineering building. What is this room number?
321.
321. It's the big classroom upstairs.
Oh, I never knew that.
I've got a list of about 5 or 6 people who've made an appointment with me. Okay. The good things to study are, of course, the exam review slides. It's not a lot of calculation. There's a little bit of calculation, enough that I'll let you bring a calculator in. It's mostly conceptual, and it's mostly making engineers write, which I normally dread. If you write something that wouldn't embarrass me, that if you said in front of a micron engineer, I generally give you some points for that. If it would embarrass me in front of a micron engineer, I may take some points off. Okay, I'm usually not too hard on the grading on these, but we'll see. Open book, open notes, let's just call it. Because you still want to try to condense some of your thoughts down into, you know, study and condense your thoughts, because otherwise it'll be a jumble of material. One guy came in here with stuff printed at the printouts of all my slides, and it was about this thick.
Or just the way that Jade would take from for a note sheet where it would just be itty bitty text.
Yeah.
You remember?
Who?
Jade.
Jade. Oh yeah. Yeah. Jade wrote really small, but she could read it.
Doesn't Jack write really small too?
Yeah, but Jack just naturally writes small. I couldn't read it. So try to condense the material down to a reasonable level and try to study. As far as the DRAM book, I would focus on chapter 2. That's probably the meat of everything that I usually end up putting in the exam, which I haven't written yet. But we're going to continue on with Kang. This is signal integrity. We probably are getting out early today because I think the end of the slides I look at and I just go, I can't talk about this because it's so outdated, some of it. And I don't care enough to update this particular portion. It's bus standards. And if you want someone to teach you bus standards, I am not the right person. I get bored to tears when I see things like that. If it's physicsy and it's something that will last forever, I'm perfectly happy to learn it. If it's something that's fleeting, I want to look it up, or I want to hire someone to look it up for me is the more reasonable thing that actually happens. So signal integrity, when we're talking about that, we're talking about the quality of an electrical signal. That means, does it look on the end of the line what you wanted it to look like at the start of the line? Digital signals, you know, we think of these as square waves. Whoa, oh, it's white. I know why it's white. Draw. I'm drawing in white because I was drawing on a black background. Digital signals we normally think of looking like this, but by the time they get down the line, they probably look, they've got some RC charging, they've got some noise on top of it, and they've got some reflections coming back, and they've got some inductance, capacitance, and resistance, which could lead to overdamping, ringing signals, underdamping, ringing signals. I don't know what I said last time. Underdamping, maybe they're really slow to respond. So all those kinds of things can happen. Now, the way we maintain our signal integrity is we invent these things called bus standards. If everybody follows the same bus standard, you're usually okay. Now, the piece of the bus standard you guys are most likely familiar with are the things like, well, with the USB, one of the pins is power, one of the pins is ground, One of the pins is serial interface. You're familiar with the pin out of those, but there's also a manual like that thick of for each one of these bus standards that defines what kind of, how much current what's the max current you have on that voltage pin. How much current can it drive? How fast can the signal switch? What the impedance is along this cable. What cable impedance do I have? There's a lot more to this standard than you guys know about. It's an 800-page document. You control F it for the things you're looking for. Make sure you're aware of things, you know, if you're actually the guy who's building the charger that plugs into the USB port, make sure you use the right type of wire for that to match the interface for this thing. Yes. Yes. Yeah. Yeah. That's not too terribly hard to do in software. The software version of that is you get the pinouts right, you get the signals right at the right time. So it's not terribly hard to do. I say that because the part I care about is what is the trace impedance? What is the Z naught? Am I going to get reflections and ringing because I'm mismatching the impedances? So there's a whole bunch of stuff that goes into these standards, more than you really think. Serial interface, the big thing I want to talk about here is serial interfaces versus parallel interfaces. The USB port we've been talking about a minute ago, it's a serial interface, which means there's one bit of data transmitted at a time. If I'm on the processor of my computer and I want to get data back and forth to memory really fast, I'll use a parallel interface where each data is like, if it's a 64-bit data word, I'd have 64 wires, each transmitting one bit of data at a time. I get 64 times the speed. But because I don't want a bundle with 64 wires in it, you guys can't see this. I'm holding up this. This is what that means. I don't want a bundle with 64 wires in it. It would be big, bulky, and expensive. I'm going to go serial here, even though it slows me down. Okay. Okay. Yes. Yeah, we had when I was up at Kip Peak, we had some of those connectors. You want me to talk about that? They were, I can't, it's painful. We had these Deutsch connectors and they're like this big around, and they were standard interface connectors to the telescope from the telescope instruments. And if someone came and mounted their instrument on the telescope, they'd be able to connect this cable into their instrument and it would go back to a power supply and other readout electronics far, far away where they were hot. And we didn't want the telescope to get hot or even get really warm. So we have these cables. They're running through 300 feet, I think it's 300 meters of telescope to get back to the power supply. Well, the company who makes the connectors decided they were obsolete. And we continued, it was such a big deal to get people to change the connectors because we'd have to get every astronomer all over the world to change the connectors simultaneously. Right, so it may involve like re-drilling and re-vacuum sealing their instruments and all this good stuff. So what we did in our infinite wisdom is we continued to use the obsolete connectors until the point where the connectors, the housing itself was like $3,000 and the pens were $200 a piece. 64 pin connector. So I come along and I come up with this brilliant idea. Why don't we have a breakout where they can put an adapter on the end of this cable and we put a modern connector on there. And that was okay, but then somebody else wanted a different cable. So I had to run a cable through the 4-meter telescope. It took me 2 years to go through the empire of cables in the telescope to be able to get permission to do that. This is what happens when you work at a big facility. Everyone has to get on board and agree. It's easier to build a new telescope sometimes. Okay, the problem with these signals are their edges. Now, this is a note to myself here because I was about ready to point out that somebody just logged in. We'll get to you later. They could have just left too. The edges on these signals are part of the problem. So if I have a 1 gigahertz clock, let's draw another square wave. It has 1 gigahertz components, it's got 3 gigahertz components, it's got 5 gigahertz components, all things like that. If I make this signal look more like a triangle wave, then I get rid of some of the higher frequency components. Yeah. A typical FR4 PCB. Does anyone know what the material FR4 stands for?
Or no, 490 said it.
I don't know. FR stands for fire retardant. That's so when we let the smoke out, the PCB board doesn't burn. It's an epoxy glass material. It's kind of it's a dielectric. But a typical PCB board has a propagation delay on those traces of about 150 to 200 picoseconds per inch. You can buy PCBs that have different dielectric constants that number might change. Now, if we're talking about, and I don't see how this is possible, Dr. Brower, if we're talking about a 1 gigahertz signal, a 1 gigahertz signal has a 1 nanosecond period, right? And if it has a 500 picosecond rise and fall time, that means the signal that I've got here looks like this. It's a triangle wave.
Yeah.
I've kind of taken that slewing of the edge to the extreme that I possibly can. A 500 picosecond rise and fall time with 150 to 200 picoseconds per inch gives me about 3 inches of PCB trace, about this yay long, is a resonant circuit. Resonant circuits are going to oscillate, which means if I send a signal through there at 1 gigahertz, it's going to just bounce back and forth and never settle down. Yeah, like that really bad mismatch problem we saw last time. The reflections last about 7 cycles. So if this is a 1 gigahertz signal, the reflections would last about 7 nanoseconds for the signal to stabilize. 7 clock cycles for my 1 gigahertz clock to stabilize. We need some kind of control over this bus to be able to get things better. The first thing is we match the characteristic impedance of my output driver to my PCB trace to the input driver of whatever it's driving. This is where the bus standards and the impedance matching becomes important. We need about, okay, to treat these like they're lump, I don't even want to talk about this. This was like a whole 490 in the fall thing. We need to keep the length, for non-RF engineers, we need to keep the length of the wires about 1/6 of the wavelength of the signal in order to minimize the capacitance and the inductance of the line. It kind of goes non-linear once you get beyond that point. Well, you get, no, if you don't keep it within that parameter, suddenly your transmission line that you think of as being a resistor actually looks more inductive at some frequencies. It looks like a huge inductor, or it may look like a huge capacitor, depending upon whether it's open or short-circuited. And I should really shut my mouth at this point because nobody understands me. Okay. So one way we can kind of get this down is, and I can't do this with a 1 gigahertz clock. I would like to point that out at this point. With a 1 gigahertz clock, you cannot create a 2 nanosecond rise time because your rise time would be longer, 4 times longer than the period of the signal. But if I could slow down the clock to the point where I could tolerate a 2 nanosecond edge, then about 12 inches of a printed circuit board, I can keep my traces down to around 2 inches without having to worry about transmission line effects. Yeah. If I go down to 1 nanosecond, then I'm looking at 1 inch of printed circuit board. That's not much. I have to put my ICs that are critical signals, I got to put them really close to each other, and I've got to keep all those lines short. 50 picoseconds, that's a ½ an inch, a little bit more than a centimeter for your metric people, and it's going to start acting like a transmission line. So we've got to care about these things, and we've got to care about what the characteristic impedance of our signal is, and not just making sure we get power connected to power and we get the serial line connected to the serial line. It's a little bit, you can do that if you're working at a really slow clock rate. With USB, we're probably not doing a 1 gigahertz clock. I have no idea what it is. I don't memorize those things because they change from year to year. I never have, and I refuse to. USB-C. Well, we got a whole bunch of USBs. We got what's the SPI and all those other things that I just tell Ian Burke in the lab, just take care. There's enough people who know how to do that. Nobody knows how to do the transmission line matching, and yeah. So yeah, if I had to figure it out, I could. I did know at one time, one particular standard. I can't remember what it is. Because as soon as I learned that it went away in 6 months, I said, this is nonsense. I'm not doing this again. That's why I'm a physics person. So for chip terminations, and you see this on some, I've seen this on some TI boards. I've seen this on an Intel FPGA board that I got, the ridiculously big FPGA board with the water-cooled stuff. Yeah, okay. The biggest FPGA board in the world. It was cool. They gave it to me for free. We need to, so for chip terminations, you see things like this on these TI boards, is I've got these wire banana plugs here for my positive and negative power supplies and ground. If you have a positive and negative power supply, you still need the ground. I've seen people do that. So I plug those into banana plugs. Now for my actual signal inputs, I've got these SMA connectors. Those are made of gold. They are rather expensive. If I had something like a digital, and this is like the gold standard for RF, literally. If I had something like a digital bus with 64 pins on it, and I had to put 64 gold connectors on it and make them up to another 64 gold connectors, it would get to be prohibitively expensive. We cannot do that. What we do this for is we do this for RF signals where we really care. This is my radio signal that I'm going to transmit in and out, and I want to keep it literally golden. Sorry. And you notice here, this is the SMA. This is 50 ohms. It's probably going to a 50 ohm cable. And right here, there's this little tiny trace off it. I'm going to switch back to white. There's this little tiny trace off of here going to a little chip resistor. That's a termination resistor to make sure that the impedance of this PCB trace and the impedance of that cable match. And it looks like there's more of a matching network in here too, because as you go along the line, there's even more resistors probably stepping it up until you get into this little transmitter chip. So every single one of these signals has its own gold connector. This is how people do it with real RF signals. As digital engineers, if you're communicating digital signals between chips, you can't do this because there's too many of them. This is the problem with the high pen count chips. It's too expensive. Another problem that we come across is, let's say I make the board and I make this trace a little bit narrower this day. We get process variations, we get voltage variations on this line, we have temperature variations. The impedance that it wants to see on that given day changes with time and temperature and who built the board and how well they built the board that day. And it depends upon the geometry, which is also varying, which is like a whole nother world of just let's make some more putts. So the way we get around this, as this is it's an older spec, but if you get the idea, you'll understand that it exists and you'll know that when you need to do this, you need to do this. And you probably just go get this high-speed analog engineering guy and have a talk with him first at wherever you're working. Hewlett-Packard, why is this no longer, oh, I know why it's not writing. Okay, had this high-speed transceiver logic I/O pad standard. It pretty much Xilinx, inside the Xilinx or the Quartus, the Altera chips that are now owned by Intel. They have a standard where you can set up the I/O pads for the particular type of bus you need. Okay, and it's programmable to meet many bus standards. Now, why did I not have to worry about this in 310? In 310, what you're given is a pre-built board with an FPGA. I really want to explain this because I explained this to people that I thought were FPGA designers professionally. What you're given in 310 is a pre-built board. It has an FPGA on it. That FPGA is communicating to the other chips and to its I/O through a set bus standard that's already been chosen for you. You can't change that. If you change that, the whole board's not going to work. So all of that's hard-coded into that particular FPGA. Now, when you're out in the whole real world, no one's going to let you use they'll let you use one of those FPGA starter boards to prototype your project. But when you want to put that into a system, nobody wants to go out and buy a Tera ASIC board and plug it into their system. What they want to do is they want to put a single FPGA chip on a board that's custom designed and interface it to the other chips. There you're going to have to pick your bus standard and you're going to have to stick to it. Don't try mixing them together. There's this horrible thing that this is real that I know about because the students ran into it last summer. Not you, the grad students. Microchip we use a lot of the microchip Wi-Fi boards because they have a lot of security dongles and add-ons and things like that. They use an SPI standard that is slightly different from everyone else's SPI standard. Because they developed it, they were competing standards for a while, and they just changed their chip to match the actual standard, but not everything got changed. You're going to run into things like that, and I actually ended up, I was the one who did this because everybody else is just sitting there going, but it's SPI, it's SPI. I'm the one who went to Microchip and said, hey, listen, we're having a problem with the SPI interface on this chip. And they said, oh, it's non-standard, you have to do this. It's slightly non-standard, you have to do this. And they gave me some code and a GitHub, whatever GitHub is. Yes, they gave me a GitHub repository for drivers that actually worked.
That's great.
Yeah, so I just told And the people doing the code where the GitHub repository was, and I looked like I knew what I was doing. Okay. I know GitHub's a thing where you share code. I don't go there.
I've actually got some things that I posted on there.
Yeah, okay, yeah. I know. I'm sure people have, but nobody would want to take, so nobody would want to steal my code.
It's always just a useful place to just store all of your previous code.
Right. Okay. Yeah, I understand that, but I just like, I remember using the word GitHub in a sentence without knowing what the heck I meant, but I, this was a few years ago. People didn't seem to argue too much with me. So, so I must have been using the word right. This is the HP single-ended output driver. Part of engineering is learning how to bluff intelligently. What I've got here, I've got some series, oh, because I'm writing in white. I've got some series input going into a buffer that has some characteristic impedance that I want to match with my output pad. And this is what it does. We've talked about something similar before. I've got one signal here that, it's white, that pulls it up. I've got another signal here that when that goes true, it will pull it down. And this is my pre-signal. This, let me change colors. This piece right here is the impedance matching part. And we talked about something like this before. Was it on your homework yet? Okay, good. So something like this was on your homework. I can directly short the input to the output and then put, and this will give me some impedance there. And I've got some stacked by powers of 2 size transistors, so I can tune the impedance with these signals, program 5 through program 0. If the impedance is set for a given bus, I just set it for that whatever impedance that bus value is and I'm done. Or I could allow it to go through and auto-tune itself. And either way, and as long as I program it for the right impedance for the right bus, or set up my FPGA so it has the correct bus standard, I'm okay. Okay, so this is how it works. We've got the calibration circuit here. This, oh yeah, you did this. This is homework 3. How could I forget that? I got all those questions. Okay. We've got this right here. There are 1, 2, 3, 4, 5, 32 different possibilities of characteristic impedance. This transistor here is like our pull-up on the last homework. Okay, I take the output from this signal, from the pad, I feed it into a comparator, and I'm comparing the output to a reference voltage. And I want to see when the output gets to be at least as high as the reference voltage is. If it isn't high enough, I readjust the signal and wait, and I just go through this loop 32 times and find out how much impedance I need here to actually get the output signal to get high enough when it is connected into the system. This can be done on the fly. So in the Xilinx, and I've kind of already talked about this a little bit, you know what a field programmable gate array is. Okay. Everyone's taken 310. Inside there, I've got these blocks, and everything, all the AND gates, the flip-flops, everything is implemented in one of these blocks. And from those blocks, I've got these I/O blocks. And the setup of the I/O tiles is going to determine what kind of bus standard, what kind of impedance you're driving there. So you want to make sure you get that right if you're putting an FPGA on a board. And anybody who ends up being an FPGA designer will do that at some point. Make sure you get the bus standard right. That I/O tile is programmable for many standards. whatever, that could be SPI, it could be USB, it could be whatever we're using today, but you would have a choice of those, and make sure you program them, make sure you actually take the time to program those for the correct bus standard. I'm not going to tell you how to do it. I'm going to tell you to control the document. I'm sorry, because it'll change in 6 months. But as long as you're aware that this exists, this will keep you from making mistakes. So this IOB diagram. So basically, when you've done this piece of it in 310, when you name a pen, very first thing you do on your module declaration is you tell it if it's an input or it's an output. And once you do that, if you drive that input or the output to the pen, it will be, okay, if this is my pad, if it's an input, I'm going to ignore this whole part right here, and I'm going to feed it into an input buffer. And it's going to compare that to a differential. It's got a differential driver there, basically. And if it's an output, I'm going to ignore that part, and I'm going to feed the output directly into the pad. So that pad itself has to get programmed for whether it's an input, an output. Some of them are both inputs and outputs, so you have to deal with that too. And in that case, you'd have the input out and output buffer working at the same time, depending upon whether you're driving the signal or going through there. Nobody cares, and this is old. Okay. This is all FPGA stuff. I don't know what it's doing in memories. Other than as, no, I'm trying to think. As a test engineer, you may have to design an FPGA. The most likely types of systems that I've seen are these data acquisition systems. And they're kind of like FPGAs, except you program test vectors into them. And what a test vector is, you have like a bundle of wires coming out. And so the test vector tells you whether each pin is high or low at any given instant in time. And the next test vector is the next time step, whatever you tell your time step to be. So those signals can all change as a function of time, and they all go to pins, little wire bundles that I can plug into cards. Probably you're in a fixed setup when you're first starting up. So those already been plugged in for you. But you know that, I have these signals going in there, and a lot of times your first job as a test engineer is just sitting there tweaking somebody else's test vectors. But I actually had to explain that to a grad student, so I thought I should talk about that. And when you get information from a test engineer, they assume that everybody knows this, is that they have test vector 1, test vector 2, and then they have signal name 1, signal name 2. It looks like a big Excel spreadsheet, and this is just full of numbers. And it used to be like it's all binary logic, and they say, here, just reproduce this. And these vectors are just literally steps in time. Yeah, I had a grad student interpret that like 90 degrees reversed. And they was wondering why things weren't working. Okay, but it's if you don't know, starting out, you make mistakes like that, and people kind of, they're patient with you until like the 3rd or 4th or 8th time. What?
I hope so.
Yeah, because you're there to learn too. Yeah, and a lot of companies too. I know Microchip, in particular, because Dylan Mills actually did this. His dad was the head of test engineering at Microchip. So when he was an undergrad student here at NAU, his dad got him enrolled in the system Verilog for pup engineers classes down at Microchip over the summer. So he got the same training as their incoming engineers, and then came back here and was incredible. I don't know anybody in Caribou, Maine. So a lot of companies do that too, is when you first come in, they will try to give you some training because you have to learn their systems and their technologies. And back when I was starting out, the most common thing to do with a new engineer is you hand them a manual, a physical paper-bound manual, say like 800 pages. Say, here, go read this. And it was kind of a test to see how much initiative you had. And if you started wandering around after about 4 hours and saying, hey, is there something I could actually do, then they might give you a job. Otherwise, I know people who just sat there and read the manual and then for like the first week. So get up, talk to people, take as many training courses as you can, and talk to people.
These guys, that kind of thing that they more or less don't really expect you to know much of anything going into the job, aside from how to learn.
Yeah, they expect, a lot of times, well, it kind of depends on where you're going to. They expect you to be trainable, or they expect you to have, oh, this happens a lot too, they expect you to have some skill that their engineers don't. Like at Gore, a lot of the engineers there are used to those Allen Bradley, horrible programmable logic controllers. They use those. They're antiquated. They work for their process, so there's no problem with them from their point of view. And to actually put a microprocessor in there's a whole bunch of newfangled ideas. But they need people who have the skills to be able to say, hey, look at this. Wouldn't this be more efficient if I did this? Wouldn't this be, and like Fallon, wouldn't this be more efficient if I use this newfangled language called C? They need young engineers to bring the new tools in and to actually update some of their older equipment too. And on that, you're going to be completely on your own, except for, you know, the technicians and people like that who can help you out. But if you can fix something like that, you're amazing. Even if it doesn't work quite right, you're still the only person who can do it. Yeah, and these are different standards. A lot of these are antiquated. Low voltage CMOS. This is TTL stuff. ECHL, I don't even want to talk about. But the single and differential ended, make sure you just correspond to the standard that they have. And there'll be people around who can help you out with this. These are very old standards. High speed.
What are all these abbreviations?
Oh, there was in the reading. It's not on the homework. That's probably on the pre-lectures. Okay,
Right, it wasn't the pre-lectures.
This is, I love, this is something that was popular back when I graduated from college, like at Auburn. That was like 87. How do you get, this is my own answer to this. How do you actually get an ECHL termination? You invent a flux capacitor and travel back to 1985, but it's an old TTL standard that you probably won't see unless you go to work at some place. There are a lot of places that have these legacy systems in there. And ECHL's just an old high speed. You may have to look it up. And I'm not going to teach this because I don't, if you have to look it up, you're going to have to review it at that time anyways. And then there's probably somebody in there who knows what they're doing. This is old stuff. Different ways I can terminate my signal. This is an FPGA. I can terminate it directly with the PCB trace. I could put a single internal termination on the line, like we saw on that TI board, that resistor to ground or VCC. I could put that right at the input pad to help match this line to what I'm expecting. I could put 2 resistors there. I could also put some capacitors there, and all those kinds of things. And there's 2 ways I can do it. This is on the board. I'm actually doing the termination on the board. This is a termination that's internal to the chip, and it's probably programmable. So this is the better option. And it's probably linked into, I'm sure it's linked into the bus standard too. Different It's this way I don't memorize these. Every single one of these has their own 800-page document. This family right here is probably amazingly similar, except they're different, like SPI and SPI microchip. So things like that. And I told you I didn't really want to talk about this. STL options. This is like, boy, this is boring.
We're getting to the point in the slideshow where you don't want to talk about it.
Well, no, I don't want to talk about it because it's
outdated.
It's outdated. I'd rather you get the understanding of what's going on in your head than to memorize a bunch of old standards. And I'm not going to sit here and update these standards every year I do this, because and they're not nearly as outdated as some of the slides I've seen 3 times. When they talk about memory speeds. Okay. So I just, well, yes, they are, because there's echo in here. I cannot say that, but I will at least tell you that they're outdated, and they're bad. Are we there yet? Oh, we're way behind. We're a week behind. I know that. So if you look at, this is like a particular FPGA. So given this is a part of a data standard for a particular FPGA, this is a table that's within there. And what you do is you Control F the bus standard that you have, and then you can find out about this, and you continue to Control F, and you do that like 335 times, and you learn everything that you can on that chip about that one particular bus standard. And then you find the little piece that doesn't work, and you Control F some more. Or if you're like me, I have the other option, is I do not mind contacting the app engineers at a company and asking them questions, particularly if I'm at the point where I've got something that sort of works and I'm struggling a little bit, or the people in the grad students are struggling a little bit. I have no problems whatsoever. Some people say I'm gonna look foolish doing this. I have no problem looking foolish if it gets the job done faster. So most companies, if you're dealing with their parts, they have different levels of service. Oh, this is so important. So I'm dealing with a microchip part, and microchip is notorious for having weird things in their circuits. They're the ones who they have the Arduinos now. The first thing I do is, I start looking through the message boards. If I'm having the problem, see if I can find somebody else who has a similar problem. And if not, I go ahead and log in and create an account, and I post something on the message board. And generally, the people who are monitoring those message boards most closely are people who work at Microchip. And they'll have a division of app engineers whose job it is to look at those. And they'll look at those, and if it's an answer to a common problem, they will usually give you a really quick answer. Here's the GitHub where you fix this, or give you a document that will help explain what's going on, either software or document. If it's something more subtle that they haven't seen before, something a little bit complex, they may refer it to one of their more advanced app engineers who will actually dig into it and see what's going on. Or sometimes they completely ignore you because they sometimes, yeah, but you can go through that. And then kind of the next level of support beyond the message boards is, especially if you're a big customer. If you're somebody like Micron and I want to buy 20 gazillion of these for this part for the SSD drives, they will get, if you call them up, they will have a person on the phone with you within 5 minutes to make sure that you actually get what you need so you can use this part. Another level of this was when I was at Motorola and we were buying 20 gazillion of everything. Motorola semiconductor product sector, I was in comm sector. I was doing the cell phones. But Motorola Semiconductor Product Sector had an office in our building. And we could go down there and talk to people directly if I just had a random question. They were kind of funny about that though. The people from comm sector thought the people from SBS were spying on them. It's all one company, right? And so we had to lock our lab doors all the time to keep the SBS people out. And they had locks on their doors too, so I don't know. But talk to the app engineers. They will help you. There are plenty of people out there who will help you solve your problems, who have the expertise. Technology is getting so complex. Nobody can memorize one of these bus standards, much less all 20 of them that are on this page. So if you run into a problem, don't hesitate to ask people. That's how I get things done faster. Yeah, and there's a whole bunch more stuff. I just start yawning. Anything in here? This is an IO standard for differential signaling. In this case, my driver, if you have a differential driver, your driver's both driving Q and not Q. This is like the digit line and the digit line not in project 2 that we'll use to drive that sense amp later on. I can terminate this by putting a parallel termination into it. And the standard is like 100 ohms, and you should have, and this is just for this particular device. And my line receiver will be differential also. So differential drivers are going to be paired with differential receivers. That's going to matter more if you're doing sensitive analog measurements. And I'm almost done. I'm actually going to get done early today. What do we have in here? Serial data transmission. I can talk about the exam a little bit, or I can answer questions about the exam or the project, either one. Many transmission standards that change monthly. DCI has the on-chip programmable impedance. One thing I would look at is make sure you understand how that programmable impedance works for the exam. Typically I put something on there with, it's got 5 transistors in parallel. Everyone's like twice as big as the next one. How would you use that to set the impedance of it qualitatively, not going through and doing all the calculations? What do you guys want to know about the exam, project, or?
Is it going to be mostly qualitative questions?
Yeah, I haven't, but I kind of,
It's also next Tuesday, right?
there, it is next
I
Tuesday.
was worried about walking here. I was like, I'm going to waste all my time walking here and the exam is today. And I'm going to have to like bust my hump back to my truck so I could drive home so I could take the test online.
The following day. It's next Tuesday.
Well, I had it backwards again. It's all in person.
Yeah.
Well, it's in person on Tuesday.
It
or you
is.
can sign up for online.
Right. Because you just have to make an appointment. Yeah. It's next week. A project. If you have questions with the right project. Okay. Probably a big ugly timing diagram. If I give you a list of signals.
Would you like some sample problems?
No. If I give you a list of signals like word line, can you identify which one's word line from the picture of the timing diagram? And can you tell me what word line does?
Okay.
And if you tell me that word line's high, I tend to get kind of upset. This is an old exam. Word line turns on the transistor in the 1T, 1C cell, allowing the capacitor you read from and written to. It goes to VCCP and allow for the VTN drop across the transistor. That's an amazingly good answer. I have gotten answers like word line high.
Word line high.
Um,
So
It's not wrong, but it's amazingly non-specific.
Yeah, wait, so what was the previous thing? Forward line has.
Thank you. Okay, what does word line do? What do all these, if I give you names of signals that you built in the project or are in the Sense amp, can you tell me what they do?
I have a question about that project, actually.
Okay, good.
Now that I think about it. In the project document, the instructions, it says to use a tri-state inverter.
Yes.
But what that means is that it'll invert your digit lines.
Yeah.
Is that still right? We should be using the tri-state inverter, not the tri-state buffer.
You can do it either way.
Because when we were in here
Oh.
like a week or two ago, and we were on the whiteboard
Yeah, you
drawing
said-
the
Yeah.
signals, I finished that project and ran the simulation. It's like all my outputs are wrong.
Oh, okay, that's all
And
right.
figured it out that it was my digit line that was being inverted. And I
Yeah.
just changed the time on that to make
Okay.
it look right. But
I called them digit line, but they're really, this is the data input. I gave them bad names on my diagram. Now the data input, you can do this one of two ways. You can put an inverter. I've seen people put 2 tri-state inverters there, which is kind of strange. Okay, and I have a right enable. Okay, and so this is coming into a bus. And there's another thing that can drive the bus. We have the word line 0 and digit line 0, array 0, I'll just call it and give it all its names, in-bit. So you have a single in-bit here that can come through and it can drive this line too. This is when I'm reading from the array. And then you have the equilibration circuit here. And this drives this line. Now, if you leave that inverter, this is the question Zach's asking. If you leave that inverter out and just run this into a tri-state inverter, what you get, the data that you write into the cell is the not of this data. It doesn't really matter because it's amazingly specific for the order that it wants you to read zeros and write ones, etc. But I don't really look at that. When I'm looking at your timing diagram, I'm making sure you have the 4 combinations. Are you reading a 0, writing a 0? Are you reading a 0, writing a 1? Are you reading a 1, writing a 0? Are you reading a 1, writing a 1? As long as those 4 combinations are there, I'm not too particular about the order they're in. Okay. Because it's really easy for me to check it, just go through, look at, I can literally look at the signal, the waveform on this line and tell you what you're doing when. It looks like a CMOS imager. Yeah, I don't even look at that. I look at those if there's something horribly going wrong with this signal here. This is where I'm going first when I'm grading them. I'm looking at the output. I know what I want that signal to look like. It's going to go VDD over 2. It's going to start out like this. You're probably going to read a 0 because you haven't pre-charged your capacitor. And then you're either writing a 0 or a 1. So this is either going to go up or it's going to go down. And then you go through and you equilibrate again back to VDD2. And then it's going to go up or it's going to go down. And then the output's going to go up or down. If you're getting the right shape of the signal on that one, I usually don't check a whole lot else. If there's something wrong with this signal and it's not working, I go back and I check the timing of equilibrate, word line 0. What's the other one? The right enable. And the data in. So those are the four signals I may check, and I may rerun your simulation and tromp all over whatever you thought you had to see if maybe you had some issues there. And then I figure out what I think is wrong and I write it down on your sheet. But if you have this basic signal on the output,
And then the one thing we actually have to like turn in on learn is the time diagram.
The timing diagram, and that needs to be turned in by 2:20 on Thursday. Everything else will be when I start grading it.
Yeah.
Which may be this week because I'm gonna have to grade your exams next week. So I may get to it early next week, or yeah. And if you have issues or if you want me to regrade it, email me and tell me to regrade it. I will, at this point in time, I will regrade project 1 until project 2 is due. And then from that point on, I will only regrade project 2 until project 3 is due.
Okay.
Unless you have an
Send you an email for project 1 before Thursday.
yes.
Okay.
Okay.
I had to go back and fix part of my project 1 because it's not compiling, it's not running, what's going on. And I realized that for my W value for my transistors, I had 0.13. There was 2 decimals and I had to go back through and take it out and recompile the sketch.
The most common thing I see is people putting in 0.13 and no U. And without that U, it thinks it's a 0.13 meter long transistor. And it just says that's way out of bounds. You cannot make a transistor that big.
Transistor. You dropped the entire world of power through that.
Yes.
Just a brick.
It's larger than the wafer.
Transistor.
Okay.
It takes 3 wafers to make one transistor.
One for the drain, one for the gate, one for the source. Okay. Yeah. Okay. All right. What is tomorrow? Wednesday? Yeah. I only have 1 class tomorrow.
I have another question.
Okay.
I'm pretty sure I know the answer to this one,
Okay.
unfortunately. For our capstone, we're working with some transistors I've been cooking with. I
Okay.
believe they're BJTs. They're the 2N222s that come with
Yes,
Arduino kits.
they are BJTs.
If
Just run the
I-
part number.
Yeah. If I put 5 volts on the gate,
It's
That's,
called the
the
base. Yes.
on the base, then on the collector and emitter still should just be whatever's there, right? The 5 volts should not flow to those.
Okay, if the base, okay, the way a BJT works, and I believe the 2N222, that one, 2N with a bunch of 2s on it, is an NPN transistor.
I think so.
Okay, so you have to have 0.7 of a volt across the base emitter junction. And you got to have current limiting resistors on all of those, the collector, the base, and the emitter. Your current limiting may be a motor, but you've got to have some kind of resistance on all of that. So you will actually drive current into the base, and whatever current's driven into the base will get multiplied by the beta of the transistor, which is a very poorly controlled number. It's listed on the data sheet as HFE, and it probably says somewhere between 10 and 200. That will be how much current you have. It's more like a current amplifier than anything else.
Well, that's kind of what I wanted to use it for, actually.
Yeah. So a small current going into the base becomes a big current between the collector and on the collector and the emitter.
The problem that I was having was that we wired the 5 volts from the Arduino into the base.
Yeah.
And then we were supposed to connect one side to the battery and one side to the Arduino. So that the Arduino would only be connected to the battery when the transistor's on, when there's power to the circuit.
Right.
So it's not draining extraneously.
Let's draw this picture. So basically okay, so you've got the Arduino here. You got to be careful here because the Arduino is going to drive 5 volts. Arduino. You want to put a resistor here. This may be like 100 k ohms or something like that. You can calculate it to get, this goes into the base of the transistor. This is coming from like a 5-volt supply.
Are we drawing a circle or my circle?
I'm kind of drawing your circuit. And then down here, you're probably trying to drive, this is called a series pass transistor. And you probably want to drive a motor or something like this. And the power from the motor is going to come off of here, but whether the motor is on or off is going to be determined by the Arduino. Okay.
What we had, what I was using it for is if you switch the 5 volts
Uh-huh.
and the Arduino,
Uh-huh.
so that when the gate gets 5 volts, when the system gets powered,
Yeah.
it should connect the Arduino and the motor. We're using a battery. We're charging a battery.
Okay.
But the problem that I'm having is that when I put 5 volts on the base, I
Okay.
get 5 volts on the emitter and on the collector. And I think I
Yes.
probably just fried.
Yeah. Okay. See, the problem is this, we got to remember this is a diode across here. It's a PN junction and this is an NPN. So it's a PN junction diode. If I put more than 0.7 of a volt, if I put 2 volts across that base emitter junction, this thing will try to drive an exaamp. We just did this calculation in 280. You've got to limit the voltage here. And the way you do that is this magic resistor right here. So you,
1.7 volts?
yeah, you've got to have a set. Okay, so how much voltage do you want to get to the motor or to the battery? Sorry,
4.1 volts.
you want 4.1 volts to the battery. So this is, if this is sitting here at 4.1 volts, what you need here is a maximum 0.7 of a volt drop here. So you want this to be at 4.8 volts. So what you have to do, how much current is this drawing?
I don't remember off the top of my head, like 50 milliamps.
Okay, so let's call this 50 milliamps. If we want 50 milliamps here, what you've got is 5, it's Ohm's law, 5 from the Arduino minus 4.8 has to equal the base current, and the base current is going to be 50 milliamps divided by beta times the resistor. And you can use that to calculate what resistor value you need to put there to get all this happening. Beta in your data sheet for the transistor, it may be listed as HFE. I don't know why they do that, but you can get that number off the data sheet. And it probably says it's minimum 20 and maximum is 200. So you just kind of do this calculation for 20, you do it for 200, and you figure out what R is, and you pick a value somewhere in the middle. And then you won't, that resistor is there to keep you from burning up the transistor.
Do you not need to do like another resistor to ground?
This is kind of resistive right here. The battery's got some internal resistance. And whatever current, and the way that these things work is whatever current you put into the base is amplified and becomes the current to the motor. So you can actually control the rate of charging with that resistor too.
But I can't control the amount of current the Arduino outputs, can I? How am I controlling how much current goes into the base?
By what's happening here is if this is 4.1, this is going to be 4.8. You're controlling the current by controlling this, you know, the voltage on this side, you know, the voltage on that side. You're using Ohm's law.
Oh, it's a BJT.
Yeah.
Okay. I wish we had a class on BJT. Because MOSFETs are super useful, but I
Right.
wish we had a whole one.
Yeah, we have
dedicated.
a whole week. Yeah, it's we need a little bit more. Yeah.
If I could take a class on BJTs instead of the ceramics class, that'd be great.
Yeah, ceramics aren't that useful. Well, they are for, and I should say that. And guess which department I'm going into? Myrna, are you here? Richard.
I'm here.
Oh, I heard Myrna. Richard, Xingyu, Nolan, and Shujuan, and Yuhao. Let's see who's, okay. You can always email me and tell me I messed up the attendance. Okay. Okay, I'm gonna stop recording.
Yeah, I think so.